Okay. So first of all, let me thank the organizer for this very nice period here and for this conference, for organizing this conference. There are a couple of apologies due. I mean, to some people that already heard this seminar, there won't be anything new, but I guess that there are not so many people that already heard it. And the second is that since this is about Frobenius theorem, and I assume that not everybody's familiar with this type of issues, so non-integral distribution of planes, I will devote some time, quite some time, to explain exactly what I'm talking about. So again, for those who already know, this is quite pointless, but I'm assuming that they are a minority. And so I apologize also to those who already know this at the basics. Okay, one more warning. Essentially, this is about distribution of k-dimensional planes in Rn or in a Riemannian manifold. But the type of results I'm going to describe are already meaningful when you are talking about two-dimensional planes in the space. So I will restrict just to this case. I will talk about distribution of two-dimensional planes, so planes in space. And the fact that these things can be generalized will not be touched in this seminar at all, okay? Because there is nothing you learn more from the generalization. There's simply the two-dimensional case in R3, two planes in R3 are already the point. Okay, so starting point is what is Frobenius theorem. Okay, let me begin with saying, okay, we have a distribution of plane. In R3. Okay, what do I mean? That at every point of R3, I associate a plane V of X. Okay, and actually this plane V of X will be spanned by two vector fields. So it will be the span of two vector fields, V1 and V2. Okay, and one important object in all this is the commutator of two vector fields. Okay, what is it? At a given point X, you simply take the derivative of this in the direction of the first vector field, in the direction given by the other vector field. So let's write it like this. Okay, forget about the X. And you subtract the derivative of the second vector field with respect to the first. If you prefer, you could write it like this. You take the gradient of the first vector field, which is a matrix, you apply to the second vector field, and similar for the other term. Okay. Okay, this is the commutator, and also terminology. So V, the distribution of plane, is called involutive. If this commutator, this is a vector field, belongs to the span, to V itself. This for every X. And same, I say that is non-involutive. If the commutator does not belong to V for every X. Of course, there is something in between. The commutator could belong to the plane for some X and not belong to others. Well, okay, let's say I'm not going to discuss this thing. So there are two situations which are clearly separators. So the situation where it's involutive, that is the commutator is always in the plane, original plane, and the situation where it's never in the plane. And the situation in between, let's forget about them. Okay, one thing, written like this, it seems that the statement depends on the choice of the two vector fields, right? But in fact, it doesn't. So this is true, no, I mean, so, yes? This, okay. So these two definitions do not depend on the choice of the vector field, okay? Of course, I also assuming at the moment that everything is as regular as it need to be. So let's say everything is C1 at least, okay? So the question that Frobenius theorem tries to answer is the following. Can we find a surface tangent to V? And by this, I mean that the tangent plane at the surface at the point X is equal to the plane assigned by the distribution for every X in the surface, okay? And here is the answer. So the statement, Frobenius theorem contains two statements. The first says that if V is involutive, then you can locally foliate the space with surfaces tangent to V. So the space is locally foliated by surfaces tangent to V. And more precisely, the foliation is a very good one, meaning that they are the level surfaces of a function of class C, whatever regularity you need. Okay, and on the other hand, so that's usually what you say, saying that the distribution is integrable, meaning finding the surfaces means integrability of the distribution. So essentially, this statement says involutivity imply integrability, and vice versa, meaning that here is the other statement. If V is not involutive, there exists no surface tangent to V. And somehow the situation in between, as I said before, I don't want to examine. Okay, and so let me just say that if the one-dimensional case, that is when you have a vector field and you are looking for curves tangent to it, that's not interesting. Because given any vector field which is sufficiently regular, you can always find a curve tangent to it. There is no restriction because that's simply the existence and uniqueness theorem for ordinary differential equation. But when you talk about surfaces, there is an issue there, okay? And somehow the problem, whether or not you can find it, is somehow solved by the commutator, by the condition of involutivity. Okay, since this is part of the only proof I'm going to present later, somehow let me start with proving. Well, to give an idea of the proof of this theorem. By the way, what I'm really interested in the following is this part of the statement. So the part about the foliation, I'm not really interested in. What's the Frobenius theorem in the title of the talk actually refers to these things. So whether or not we can find surfaces tangent to a non-involutive vector field. Okay, so that's what I will focus mostly about later. But okay, let me at least give an idea let's say, of the proof of this, but you realize it's the proof of the entire theorem. So okay, you can restrict without loss of generalities. I mean, it's a local theorem, right? So you can restrict to the case where V has a very specific form. So you can assume that V1, so you write R3 as R2 times R, meaning that you, a point in R3, you actually separate the first two variable and the third one, okay? So, okay, this is the vector of the first two variable. And so you can assume without loss of generality that V1 of X is of this form, 1, 0. And here is some vector function. And that V2 is of this form. Okay, without loss of generality means that I'm actually assuming that my distribution of planes has a non-trivial, I mean, is not orthogonal to the horizontal plane, but locally it's safe to assume so. Okay, and then I write specifically as the span of these two vectors, which I can do. Also, with no loss in generality, I can assume that the surface S is the graph of U. Which is a function from R2 to R. Okay, again, of course, not all surfaces are graphs, but I can always reduce to this. So what does it mean that now I have a point X here, I have my tangent plane here. Now, this will be, the projection will be X prime. And now the vector field V1 and V2 are essentially the one whose projection, so this would be V1 and this would be V2. So the projection of V1 will be the first coordinate vector and the second will be, okay? So essentially 1, 0 is the projection of the first vector and 0, 1 is the same. So what does it mean that the surface S is tangent to this plane? It means that the partial derivative of U in the first direction is W1. And the partial derivative of U in the second direction is this one, right? So V S tangent to V at X is the same as saying that the gradient of U in the point, well, in the point X prime, okay, in the projection, is equal to the vector field W, whose components are these two. Computed at X, which means at X primes, U of X prime. And now we are getting back to something. Okay, if you were not familiar with Frobenius theorem before, now we are getting something close to something that we all know from calculus, right? So essentially, finding a surface means finding a function U whose gradient is prescribed. Not exactly in the classical version of calculus, where prescribed means it's a given vector field. This is a vector field that depends on X prime, but also on the value of U itself. Yeah, fine, but it's not really different. And so then if this holds, let's say this holds, let's say we found a surface tangent to V, capital V. So this identity holds. Now I take the curl and I should find out something, right? Because that's exactly what qualifies the curl of a vector field of a gradient is 0, right? So that's, okay, so now you take curl. And the curl of this is 0. because it's a gradient. Now, if you compute this one, okay, you have to do, I mean, you have to do some computation, but what you get is okay. So when you derive, okay, you have to take the first component of this, derive with respect to the second variable minus blah, blah, blah. So if you do it, when you derive this, the first component of this, with respect to the second variable, you obtain this, but you also obtain something coming from here. So it's not the usual curl. And you multiply by the derivative of this with respect to the second variable, okay? Which happens to be W1, sorry, W2, okay? And similarly, now I take the derivative of the second component with respect to the first variable, and I obtain this one. To the x3. And now it's an algebraic computation. You find out that this is the wedge product. This is V1, wedge V2, wedge the commutator. Or if you prefer, it's the scalar product. Well, okay, this should be a 3-vector. The 3-vector, it's a number. If you prefer is, or it's the same as, if you prefer is, you take the vector product of these two and the scalar product with the third one, with the commutator. So now what happens is that if we have, a surface which is tangent at x, in that point, this has to be 0. So this has to be 0. And this means that this vector is orthogonal, sorry. This vector is orthogonal to this one, but this is normal to the surface. So this vector is tangent, sorry, this is normal to capital V. So if this is 0, this means that this belongs to capital V, okay? So bottom line is that let me write it. Okay, you can write it in the way you prefer. Okay. And okay, so this is the basic computation and tells you more or less everything you want to know. Okay. Well, let's say at least gives you a proof of this, right? Because now I have that, in fact, I have a stronger result. If V is not involutive, there exists no surface which is tangent at any point. Notice, however, that there is an issue about regularity, which will come later. And the issue about regularity is the following. In order to run this computation, I need to know that U is of class C2, because I'm taking the curl of the gradient. C2 or something like that, two derivatives, Sobolev if you like. But the proof doesn't quite work if I only know that U is of class C1. And this is a real issue, it's not a matter, I mean, as we'll see in a second, that's what matters. So really this proves, I mean, the rest of the computation are okay under very mild assumptions, there's assumptions which are natural. So my distribution of planes, so let's say in the following, these are regular. I don't care, I mean, about the case where they are not regular. But what I care in the following is how regular is the surface S, that is, how regular is U. And so in this proofs, I really need U to be of class C2. So the surface S has to be of class C2. Otherwise, the proofs does not work, okay? And, okay. So now, let's go back to the to what we want to do. So by the way, this, keep it in mind because it's somehow in the following, I will always assume that this setting, so that the surface is represented by a function and the vector fields out of this special type. Okay, so this remains also for the following. Now let's go back here. And I don't think I need something. Okay. So what is the question now? So does Frobenius theorem holds for weaker notion of surfaces? Okay, and well, this is some very vague question. I have to make it more precise. I will make it more precise. Let me give a quick motivation for this. The original motivation for this was the following question in geometric measure theory. If you have, well, a two-dimensional current in R3, which is of nice type, let's say normal current, can you foliate it? That is, writing it as superposition of rectifiable currents. I mean, so you have some general object of abstract type, and you want to show that in some sense this is just a superposition of surfaces in the sense of, well, rectify what integral currents are. Okay, and somehow it's interesting for various reasons, because it essentially, a positive answer to this would reduce the problem of finding a minimal surface in the setting of currents to a convex problem. And solving a convex problem is always better than solving a non-convex one, essentially because whatever you do, you end up in the minimum just moving through along the gradient. Okay, so there was this issue about, is it true that this abstract integral normal currents can be written as superposition of surfaces? And in some sense, this is Frobenius theorem. Well, it turns out that the answer is no. Okay, so there's no surprise there. This has been known for a long time, but somehow there are questions related to this issue. So that's the origin of all this, but I'm not going to discuss that today because there's simply no time. Okay, so let me start with this type of question. So the first one that I would like to address is the following. Okay, so this is an example of how this question can be made more precise. So take S and V and S as before. In particular, it could be that setting over there. Okay. And you ask yourself, okay, I take the set of points where S is tangent to V. Okay. So let E, including an S, be what is called the contact set. So this means that for every X in E, the tangent to S is the for every point in E, the tangent to the surface is actually the plane. Okay, so it's where the surface is tangent to the distribution of planes, right? So the question is, how large can E be? So from now on, okay, sorry, let me state it from now on. I assume that V is in non-involutive. Okay, this is important. From now on, V is non-involutive. So E is a contact set of S. And now the question is how large this can be. So E cannot be the entire S. That's Frobenius theorem. E cannot be open, because if it is open, well, E is a surface in itself. But what about E when it's not open? So first question is how large? Certainly E can contain a curve, because I have my distribution of planes. I construct a curve which is tangent to this distribution of planes, which I can do. I mean, I choose any vector field in the distribution, I integrate and I get a curve. And then I can extend arbitrarily this curve to a surface that will be a contact set, the curve. So it can be a curve. How large can be? And in particular, can have positive area. Can I have positive area? So I'm trying to show that under certain assumptions, so this is the question I want to discuss, right? But then of course there are finer questions where you discuss, well, let's say it doesn't have a positive area, how large can the dimension of E be? Okay, but let me stick simply to, I restrict myself to the simplest question. Can it have positive area? And the answer is, it can. So here are some results. Okay, let me say that from now on, when I say Frobenius theorem holds, I mean this is not possible. Okay, so I write this. This simply means that this area is 0. Okay, because that's what should happen if you believe in Frobenius theorem. You have a non-involutive distribution, then the contact set cannot be large in the sense that it must have area 0. So from now on, when I say Frobenius theorem holds, I mean that I can prove this. Okay. So this is the meaning. Okay. Okay, and here are the results, known results. So the first one goes back to Balog, Zoltan Balog. Okay, let me say that this question has been addressed by many people, okay, in different forms. And each person had his own favorite notion of surface. Okay, let me mention at least, I mean, making a full list would be complicated. Let me mention Zoltan Balog. And Valentino Magnani also worked with surfaces that are mostly images of Sobolev function. Okay, but somehow this question has been somewhat around for some time. For reasons that are not entirely clear to me, they all work in the setting of Heisenberg group, but there is nothing about this problem related to Heisenberg group or group structure or anything. So I think it's simply due to the fact that that's the community they came from. So their results holds without any assumption of group structure or anything. Okay, it's simply the setting that I described is what you really need. Well, no, wait. No, I mean a distribution of two planes in R3. It's in that sense. No. No, come on, not going to matter. No, but I'm saying that they are adding some. They always assume. Many people assumed a group structure which is not really there. I mean, this is a matter about Carnot-Karateodori type of problems, not groups. Group structure doesn't matter. And their proofs works essentially without any assumption of, I mean, the group structure is there because they simply forgot to take it away. If you look at the proofs, they don't really use it. Okay, so Balog, and he says that, well, says two things. So if S is of class C11, then Frobenius theorem holds. Every contact set must have measure 0. So, well, that's slightly less than C2. Not really less than C2, you might say, okay? But he also proved in the same paper that if it is of class C1 alpha, with alpha less than 1, then Frobenius theorem may fail. So he gave example of surfaces of class C1 alpha such that the contact set has positive area. Okay. OV is smooth. Let's say, I mean, it doesn't really C1 for all purposes. Usually, well, let's say that that's what they assumed implicitly in the Heisenberg group is that it's smooth. But what we need is C1. So from now on, V is, yeah, V non-involutive and C1. Yeah, I think so. Yes. Okay. And this is Balog. And then there is, however, this third result that I would like to, and this is actually, you have to put it together two papers of the Ladia, 12 and 17. And he essentially proved in these two papers, but you have to put together the results, that if you assume something about the regularity of the contact set, then you can, the result is true. So if U is just of, is S is of class C1, but now I'm asking something more about the contact set, regularity of the contact set. And so the contact set is, and now forgive me, finite perimeter set. Means that the boundary, well, can be bad if you look at it as a set, but it's not too bad in the sense of distribution. So this is a notion of regularity of the boundary. Okay, just take it as this finite perimeter set. Then Frobenius theorem holds. And somehow this results simply saying that I like to read these results as this. Either you have a certain regularity of the surface, or if you take away some regularity of the surface, you can compensate with regularity of the set, of the boundary of the set. Okay? So I would like now to explain a little bit, because this is really the core of the matter. How comes that C11, this proof essentially works, while C1 alpha doesn't? Because that's what, okay, so when Balog proves the first statement, statement 1, is essentially this proof here, okay? And so I want to simply go through this proof again and see why C11 is okay and why C1 alpha is not okay. Where is the difference, at least? I mean, so where the proof breaks down if U is of class C1 alpha. And okay, let me write this in a different, slightly different way. So this is W computed at X prime U of X prime, and I subtract the gradient, computed X prime, and I say this is 0. Okay. Now let's say that I compute the curl of this quantity. Let's call this F. Okay, this is a vector field in R2, and I compute the curl of this, which I can do in a sense of distribution. So there is no problem. And if I compute the curl, well, it's the same computation as before. I'm just saying that you can do it in the sense of distribution, because even if this is 1, still the distributional curl of this is 0. Okay? So you can't compute the curl of this in the pointwise sense, but in the sense of distribution, you can perfectly do it. And it's 0. I mean, it's nothing strange there. It's a linear operator. You can do whatever you want with distribution. Okay? So what you get here, you get what you get before. So you get, well, let me write it like this. B1 wedge B2 wedge the commutator. Computed, so this is computed at x prime, because f is a function of x prime. This is computed at x prime, u of x prime. Okay, so these are defined on the space. So they are computed at this point. This is computed at this point, okay? But despite this, this identity holds. So this holds in the sense of distribution. And I need distribution when I compute the curl of this. This is no problem here. This is a pointwise computation, but this one has to be computed in the sense of distribution. Now, what you would like to say is that if f is 0 on a set, so now we go. Okay. So now if E is a tangent, is a contact set, means that this quantity is 0 for every x prime in the projection of E, which I call E prime. So remember, this is a contact set that lives on the surface here. I project it down. That's E prime, okay? And so what you would like to say is something like, okay, since this is 0, f is 0 on E prime, then the curl must be 0 on E prime. That's the type of statement that you would like to have. Okay, and here is the catch. The fact that the vector field is 0 on a set, if the vector field is sufficiently regular, implies that the curl is 0 on the set. And that's exactly the result, first result, I mean, of Balog, which is, I mean, easy, is that simply, so the question is essentially the following: does this imply that the curl is 0? And let's say almost everywhere. Let's say it doesn't, in this case, it's, well, it continues. Okay. And here is exactly what is not true in general. If you have a vector field which is not sufficiently regular, then this locality property holds. If not, if it's not sufficiently regular, it does not hold. Okay. So let me state more precisely what I mean by locality. Okay. So definition. So let T be a linear operator, a differential linear operator. Constant coefficients, I mean, for what? I mean, we're talking about the curl, okay? So if you like first order constant coefficient, but doesn't really matter, at least for the definition. Okay, so we say, and consider, so we say that T is strongly local if the following holds. For every function f, let's say in L1 lock, so the minimum to compute, well, to compute the distribution, the T of f, such that the operator is also in L1 lock. Do I know that if f is 0 almost everywhere on a set, then also the operator has to be 0 almost everywhere in a set? So there holds the following implication, that if f is 0 almost everywhere on a set E, well, on a set A, then the same is true for and this, let's say, for every Borel set. Okay, if it's an open set, that's no problem. It's what distribution do very nicely. On open sets, clearly, this is true. Okay, if a distribution is 0, whatever linear operator you compute is also 0 on an open set. But if it's not open, it's not completely obvious. So I'm assuming this both in L1 lock just to say that this statement makes sense and this statement makes sense. Okay, but then the question is, so this object, yeah, and the question was whether the implication holds. And so what is known is that the gradient is strongly local, but the curl and the divergence, for example, are not. Okay, so for example, okay, and the gradient is strongly local. It's a well-known fact about Sobolev function, essentially due to the fact that every Sobolev function is differentiable in some approximate sense almost everywhere. Now, if it is 0 and you take a pointwise differential, because that's what approximate differentiability means, that essentially you compute the differential as you would do in the classical sense. Well, then if it is 0, this is 0. In fact, if it is constant, the gradient has to be constant, okay? Because you are differentiating a function which is 0. But here is the problem. When I take curl and divergence, I'm not assuming that the curl, I'm only assuming that the curl is in L1, not that the entire derivative is in L1. Of course, if the entire derivative is in L1, also, and then the gradient is 0, then also the curl is 0, clearly. But I'm not assuming that in this statement that the curl is in L1. So that's, and this is something that I proved at the very beginning of my career. Okay, so it's essentially saying this part. Okay, and this is exactly the problem. So the problem here. There is not enough regularity assumed a priori on U. So let's say when you go through this implication over there, you see that you would like to have the strong locality of the curve. Now, if you assume that the surface U is of class C11, sorry, that U is of class C11, then F is of class C1, sorry, C01, which is W1 infinity, okay? And that means that somehow you can use the locality of the gradient. The gradient is 0, then the curl is 0. But if you are only in C1 alpha, then your F is in C0 alpha. That's not a Sobolev spaces of order 1 in any sense, not a W1 something. And so this implication does not hold. Okay, and that's how the things works. Now, since I'm close, let me say simply, let me add what we did. Okay. And then I will close because sorry? Is the same, yeah. Well, wait a second. For the gradient is the same. So the question is whether the P different than 1 makes a difference. It seems it doesn't in this type of questions. Meaning that, yeah, it seems it does not make a difference in this type of question. So I put, to be honest, I put L1 simply to put the minimal assumption. Okay, so differentiability results for Sobolev function also holds for W11 function, but are not those that you prove really using the harmonic analysis representation of Sobolev function. So if you get classical books on Sobolev spaces, which are mostly based on the harmonic analysis point of view, sometimes you realize that the case P equal 1 is not treated because it gives problem, but not for this type of properties. Okay, so new results. So the first, this is with Andrea Merlo and Annalisa Massacesi. As new, not really new because we have it since 4 years or something, but there is, okay, I'll tell you where we got stuck. Okay, essentially this is that it's an interpolation of this and this. So you would like to say that if you drop some regularity of the surface and you add some regularity of the boundary, then the result still holds. Okay, so interpolation between these two. And this is the result. Let's assume S is of class C1 alpha with some alpha less than 1 and larger than 0. And now you add some assumption on E. One people says it's some fraction of the perimeter is finite. Let me say in terms of Sobolev spaces. So I have a derivative of order 1 minus alpha, something less than a full derivative, which is say in L1. Okay. And lock, because this is a local problem. Then Frobenius theorem holds. But somehow what is more interesting, I think, is that, which we found, this we were not surprised at all, but somehow what we found a bit surprising is that if there is a certain regularity of this, then you don't need any regularity. So it's enough to have a certain fractional regularity of this in order to get the results without any regularity. So this is just C1. And this is in a fractional Sobolev spaces with S larger than 2/3. Well, I'm not sure about this, okay? Then Frobenius theorem holds. So it appears that somehow this is not sharp. It's enough to have a fraction of okay. Sorry, 1 minute. Okay. And then there are counterexamples. But here is the problem. So if S is C1 alpha, in general, some regularity is needed. Okay, what does it mean? It means that we have counterexamples showing that with surfaces of class C1 alpha, we have sets with a certain Sobolev regularity, but not the one prescribed above, that have positive measure and are contact sets. So we have counterexample. Unfortunately, the examples here do not match the bound here. And you can clearly understand why. This is one proof. This is a different proof. And there is no reason why these two proofs should give the I mean, you have two different proofs and you expect that they give the optimal results. I mean, if you're lucky, yes. So what we think at the moment is that the results are not here. The counterexample do not match what is written here, simply because what is written here is the first things that we come up with, right? That there should be some results that actually interpolates between the two proofs and gives something, but we have no idea how to do that, okay? And yeah, but okay, let me say what this all comes from is this type of results. It's the locality. It's what we prove is actually that, well, let me say in words, that this implication holds under some assumption on the boundary of E prime and on the regularity of V. Okay, so that's somehow this whole these two results follow from results on the locality of the curve. So on locality, and I'm gone over time, so I will not describe. Implies 4 and 5. So what's really, I mean, what I'm saying is that in the end, what you really work on is the locality of this curve operator. And yeah, okay, I think there is no time to go beyond this. So sorry for the overtime, and this is it. Thanks.